the video lecture that we did last week, we started talking about partial derivatives and what do they mean. First of all, we said that if z is a function of two variables, then we write the partial derivative of f with respect to x, or we use this notation, partial f, partial x, because f is the function z. Sometimes we say this is partial z, partial x, and there are a few other notations, but these are basically the one that we're going to use the most often. And then the partial derivative with respect to y is equal to partial f, partial y, or the partial derivative with respect to y of f of x y, or partial z, partial y. So what is the geometrical meaning of this? Let's say that the function f of xy represents z is equal to f of xy represents some surface S in 3 dimensions, right? Now let's choose a point AB, which is part of the domain of the function f, okay, on the xy plane, and then the point P, evaluated as ABC, belonging to the surface, right? So just evaluating f of AB, okay? And then let us intersect this surface by a plane, this plane here, which is going to have value equation y is equal to b, okay? So this plane right here is parallel to the xz plane, okay? And that goes through the point AB and goes through the point P with coordinates ABC, okay? The plane y is equal to b crosses or intersects the surface S at the curve C1, okay? So this curve C1, if we think about it, C1 is represented by a function in one dimension, okay? Why? Because I'm taking y to be a constant, then C1 is represented by the function f of x b, okay? So let's call this function g of x, right? So now this curve depends only on x. Why? Because we have taken b as a constant. We have fixed b, okay? So what is going to be then the partial derivative of f with respect to x? Is nothing else, but it gives us the slope of this curve C1 at any of these points. So the partial derivative of partial f partial x and partial f partial y geometrically are interpreted as the slopes of the tangent lines crossing through the point PABC to the traces C1, and then if I take this plane right here, which is x is going to be equal to a, okay, I'm going to obtain this curve C2 that will have slope tangent line T2 at the point P. Okay, the slope of this tangent line is going to be given as partial f partial y. Okay, so just a reminder, how do we find partial f partial y? When looking for partial f partial x, we treat y as a constant, and we differentiate the function in two variables only with respect to x. So for example, find partial f and partial y for the functions f of xy is equal to x plus sine of y. Okay, so partial x partial derivative with respect to x is going to be what? So now I treat everything that depends on x, I treat it as a function. Everything that depends on y, I treat it as a constant. So sine of a constant is a constant, and derivative of that constant is 0. Derivative of x is just 1. Partial f partial y. Now I have function sine of y, and its derivative is going to be cosine of y. Because I'm finding the derivative with respect to x, with respect to y, I treat x as a constant, so the derivative of a constant is 0. Second example, let's say f of xy is equal to x times sine of y, right? Now partial f partial x is going to be equal to derivative of x is 1, but now I have a multiplication. So a constant times derivative of a constant times a function is the constant times the derivative of the function. Derivative of x with respect to x is 1 times the constant sine of y, I get sine of y. Similarly, partial f partial y, now the function is sine of y times x, because I'm looking for the derivative with respect to y, I treat x as a constant. So the derivative of a constant times sine of y is the constant x times derivative of sine of y, which is cosine of y. Okay? Let's see another example. F of xy is equal to x plus y times sine of xy. So here we have product rule. Okay, so be careful. Partial derivative of partial f partial x is equal to first the derivative of this multiplicand, where x is a function of x, so derivative of x is 1. This is a constant because I'm differentiating with respect to x. So derivative of x plus a constant is just 1. So you get derivative of x plus y with respect to x is just 1 times sine of xy, so sine of xy, by the product rule, plus this term right here, x plus y, times the derivative of sine of xy. So here I have to use the chain rule. Derivative of sine of xy is cosine of xy times the derivative of x times y. Because I'm looking for the derivative with respect to x, I treat y as a constant, so the derivative of x times a constant is just that constant, so y. Similarly, partial f partial y is going to be equal to, well, here I can use even some kind of symmetry, but let's go step by step. Derivative of y is 1, derivative of x with respect to y is 0, so 0 plus 1 is 1, times sine of xy, I get sine of xy, plus derivative of sine, plus this term here, x plus y by the product rule, times derivative of sine of xy is cosine of xy, times derivative of xy with respect to y. Derivative of, and here, a constant times y, the derivative of a constant times y with respect to y is just the constant, because the derivative of y is 1. So, times x. Okay, let's do a few more examples. Let's look at the function f of xy is equal to x over x plus tangent of y squared. Okay, so here obviously we're going step by step. First we just had derivative of a sum, then derivative of a product, then derivative of a product and including the chain rule. Here we have derivative using the quotient rule, right, plus the chain rule when we differentiate with respect to y. So partial f partial x is equal to this function here. We have to use the chain rule, so we square the denominator right away. X plus tangent of y squared squared, okay, then the derivative of x with respect to x is just 1. So the derivative of the numerator times the denominator. So 1, derivative of x is 1, times the denominator, x plus tangent of y squared, minus x, the numerator, times the derivative of the denominator. In the denominator, what do I have? Derivative of x is 1. Derivative of tangent of y squared. This whole expression here doesn't depend on x, so it's treated as a constant. Derivative of a constant is just 0. So x minus x cancels out. Partial f partial x is just tangent of y squared over x plus tangent of y squared, then the whole denominator squared. And then partial f partial y, okay? Because variable y exists only in the denominator, this whole expression can be written as x times x plus tangent of y squared to the power of -1, right? And then I look for the derivative with respect to y, okay? So let's see, what do we have? X is being treated as a constant because I'm looking for the derivative with respect to y. So a constant times a function, derivative of a constant times a function is the constant times which is equal to x times -1, the exponent drops down, x plus tangent of y squared to the power of -2 times, by the chain rule, oops, sorry about that, by the chain rule of the expression here in the parentheses. So derivative of x is 0 with respect to y, and then derivative of tangent is secant squared of y squared times, by the chain rule, to y. Okay, and then this can be written as -2xy secant squared of y squared over x plus tangent of y squared, the whole expression squared in the denominator. Okay, so let's do question E. Okay, let's say that the plane x is equal to 1 intersects the paraboloid z is equal to x squared plus y squared in a parabola. Find the slope of the tangent line to the parabola at the point 1, 2, 5. Okay, so we learned about these paraboloids. Oops, sorry. Okay, and then I have at the point here, I have 1, there is a plane x is equal to 1. This plane is parallel to the yz plane, sorry about that, and it intersects the paraboloid in this parabola. okay? So basically we want to find the slope of the tangent line at the parabola 1, 2, 5, at the point 1, and then here 2, at this point here. So this is the point 1, 2, 5. So what did we say? If we are intersecting the surface with the plane parallel to the YZ plane, that means we are looking for partial Z, partial Y at the point 1, 2. So partial Z, partial Y, well, this is a very simple expression to differentiate with respect to Y. This is a constant, right? And then here the derivative of y squared is just 2y evaluated 1, 2. 2 times 2 is simply 4. And then we'll do one last example in this video that will deal with functions defined in 3 variables, and the logic is the same. So if you have f of x, y, z is equal to x times sine of y plus 3z, okay? Now you have partial f, partial x, partial f, partial y, and partial f, partial z. The logic in evaluating these derivatives is the same, because here I'm looking for the derivative with respect to x. Everything that doesn't depend on x is being treated as a constant. So for the first derivative, look at this, sine of y plus 3z. This whole expression doesn't depend on x, so that's being treated as a constant. Derivative of x with respect to x is 1 times the constant is just the constant sine of y plus 3z. Now partial f, partial y, x and z are being treated as constant, so derivative of a constant times sine of some function in terms of y is the constant times the derivative of sine, which is cosine of y plus 3z, times the derivative of y plus 3z with respect to y. That means the derivative of y is 1. The derivative of 3z doesn't depend on y. That means it's being treated as a constant. The derivative of a constant is 0. So times 1, or just this expression right here. And similarly, partial f, partial z, x is a constant, cosine of y plus 3z, because I'm looking for a derivative with respect to z. Y is being treated as a constant, derivative of a constant is 0, derivative of 3z is 3.